set during a flight that lasted just over 2 minutes. It is hard to resist invoking another pair of independent tinkerers, Orville and Wilbur Wright, when writing about Reichert and Robertson. Like the Wright brothers, the two men, who met as engineering students at the University of Toronto and now run Aero Velo, their design and innovation lab, share a passion for manned flight. Reichert says that they want to inspire people to see how much more we can do if we really prioritize efficiency. That's why they mostly use materials that have been around for decades, such as balsa, styrofoam, and mylar, and why they embrace the limitations of working with human power. It means they cannot go and buy a better engine, Robertson says. You have to solve your problems without changing your power supply. You can't just increase it. And surely bicycle shop owners Wilbur and Orville would appreciate the central role of the bicycle-powered flapping wing aircraft called an ornithopter. But the most Wright-like thing about Reichert and Robertson is their method. The Wright brothers were mechanically inclined, Reichert says. They knew how to tweak things and fix things, but they were also scientifically rigorous, which is really the combination that you need. The two Canadian engineers are not helicopter designers, which is why they were ignorant on the scientific papers dooming them to futility. What they did know, however, was that the complex computations they had to do would potentially require hours and hours of expensive supercomputer time that they could not afford. And the duo felt their software needed to improve on the conventional approach to aeronautic design, in which the structural and aerodynamic components are developed by separate teams and handed back and forth. That process, Robertson says, results in a solution that is not perfect from the aerodynamic side and not perfect from the structural side. To address all these issues, what they needed was a program that would simultaneously merge the structural and aerodynamic elements of design parameters that were specific to human-powered helicopters. It also had to be cheap to run, and fast. So they created one on their laptops in a 5-month code-writing marathon that in part drew on earlier work Reichert had done for the ornithopter, which had earned him his Ph.D. To get from an unaffordable supercomputer to a laptop, they decided to forego high-fidelity modeling capacity in favor of medium-fidelity models of things such as airflow around the rotors. High-fidelity code can provide precise details about what's going on where the aerodynamics are very complex, like at the tip of the rotor. But although that standard's necessary for commercial aircraft design, it was not required for the low, slow, readily modified Atlas. Medium fidelity will always allow you to get within, say, 2% of the correct answer, Robertson says, and that's really what we're looking for. Their custom program enabled them to test almost any given helicopter design on their laptops. They just plugged in the dozens of variables for a proposed design, such as rotor geometry and the weight, dimensions, and failure modes of the construction materials, such as carbon fiber tubes. The program crunched all those data and, in a matter of minutes, spit out the optimal version of the given aircraft and the minimum amount of power needed to get it airborne. The code's now being used in NASA's software library because the agency liked the way it got very close to the correct answer very quickly. The first design decision Reichert and Robertson made was to go big, long arms and big rotor blades to maximize lift. Watching the video of Atlas's winning flight, its rotors, turning at just 10 revolutions per minute, may seem too slow to be effective. But it is their huge size, not their speed, which supplies the lift that gets the machine off the ground. The previous failures, the two felt, artificially limited the size of helicopters and rotors to make them fit in places like gymnasiums because wind gusts outdoors would be too much for these delicate aircraft to handle. Staying inside was smart, the engineers agreed, but gyms were too small. That's how a cavernous old barn north of Toronto and then the soccer center near the same city became the Kitty Hawk of human-powered helicopter flight. The other major design constraint for Atlas was the weight and power capacity of its engine. Reichert, a shade over 5 feet 10 inches.